particularly right now we were trying to work on the problems. So here is another problem for you, where you are having two masses, and then they are connected with springs. The masses are connected with springs of stiffness K. And at the same time, the masses are connected with the supports with the same spring stiffness K. So if you write down the equation, it will come as mx1 double dot plus 2k kx1 minus kx2 equal to 0, and then mx double dot mx2 double dot plus 2kx2 minus kx1 equal to 0. And then if you write down it, the equation in the matrix form, this will come as m0 0m, then acceleration vector plus 2k minus k, then 2k x1, I mean the displacement vector. So you see that because of using the same springs everywhere, we are not only getting a symmetric matrix, but we are getting a doubly symmetric matrix. You see, the mass matrix is having symmetry about both of the diagonals, and at the same time the stiffness matrix is also having symmetry about both of the diagonals. So can you now just try to solve this problem? I mean, try to find out the frequency and then the mode shape, just in the same way we did in the last problem. In fact, this will be more easier. It will be easier for you to handle with the numbers because they are of much more uniform nature. You see, you have to substitute. See, since we are considering the modal vibration, that means we have to substitute x1 equal to u1, x1 equal to u1 f1t, x2 equal to u2, sorry, x1 equal to u1 ft, and x2 is also equal to u2 ft. That means u1 and u2, the shape defining terms or the proportional displacement defining terms, they are different, but the time function is same for both the cases. That means you see, instead of the double derivative, you can substitute x1 double dot equal to u f double dot t, and the u1 f double dot t, and then x2 double dot equal to u2 f double dot t, isn't it? And then you see that instead of using n minus 1 solution, that means here n solutions, that means here n equal to 2, that means instead of using 2 solution, you should require instead of n, you should require n minus 1 solution, and all the variables are expressed in terms of one variable, because n minus solution, one number of solution cannot be sufficient for solving n variables. So you have to express the n minus 1 variables in terms of the remaining variable. So, and then that's how you will get the coefficient of the remaining variable, and those coefficients will define the shape, while the remaining variable will have the coefficient 1. So that way you will get a vector if you just collect all of them, and that will be the mode shape vector, or mathematically speaking, that will be the eigenvector. You see that we have substituted x1 equal to u1 f2 and x2 equal to u2 f2 ft. So f double dot t equal to minus omega square ft, because and then once we substitute this, f double dot t equal to minus omega square f t came from this equation previously when we talked about this equation, you know, mm, yeah, ft equal to, say, ft takes a form ft equal to c cos omega t minus phi, and therefore f double dot t becomes minus c, then minus c omega uh, cos omega t minus phi. So uh, after this, uh, you see, when we substitute this, so we get the actual form of the eigenvalue problem: 2k minus omega square m minus k, then 2k minus omega square m. The problem is, you see, the characteristics of the eigenvalue problem is that in the diagonal terms, in the major diagonal, there should be the same quantity. You can, as a whole, call this as lambda, that this should be subtracted. The same quantity should be always subtracted from all the diagonal terms. So here, uh, and then for a non-zero solution, the determinant of this matrix will be equal to 0. So this is equal to 0, and then we get omega square. I mean, just simply solving the quadratic equation, we get 2k over m plus minus k over m. So it comes omega 1 square equal to k over m, omega 2 square equal to 3 k by k over m, and that's how the omega 1 and omega 2 become the square root of these quantities. So when we substitute omega 1, then we get the first mode shape, and then we get the ratio between u1 and u2. Even if we take the first equation, then also we'll get it, and if we take the second equation, then also we get it. We need only one equation, because as I was telling, that two equations. So here, what we for non-zero solution, what we need to do is that the uh, remaining n minus 1 variable will be n minus 1 variables will be expressed in terms of the remaining nth variable, and therefore the ratio we get u1 by u2 equal to 1, and here we get u1 by u2 equal to minus 1. So now can you tell me anything about the physical significance of that? You see that in the first mode, that means the first mode is a vector 1, 1, isn't it? And then it can be multiplied by any quantity, and that will be a solution. So it's having infinitely many solutions. Only thing that the proportionality is being maintained. That means the ratio between the displacement u1 and u2, that should be maintained. So whatever amount the first mass is going, the same amount the second mass is going. That is happening in the first mode, isn't it? And in the second case, what is happening? It is just opposite. That means whatever distance the first mass is moving on the left hand side, the same amount, but in the opposite direction, the second mass is moving. That is on the right hand side. Okay, or otherwise, that means if the first mass is moving on the left hand side, then the second mass is right hand side, or vice versa. Uh, so they are moving in the opposite direction. So physically, if we just can you give any physical interpretation? You see one thing, that In the first case, U1 by U2 equal to 1. That means both the mass are moving together. That means there was a spring in between these two masses. So that spring is not undergoing any extension or compression. That means as if we can consider that there is a rigid link between these two. You see, we may consider it like this, that there is a rigid link between these two, and these two are moving like the same mass, and then there is a 2m mass which is moving with a 2k stiffness. Are you getting me? That means here if I put a spring K, here if I put a spring K, then what I'm doing? Am I putting them in parallel or am I putting them in series? Can you tell me? You see that when we are putting the two springs in parallel, that means both of them are opposing the motion. Okay. So that means the summation of the stiffness of both of them are opposing the motion. Let's try to understand. Okay, and then the displacement is common for both the springs. On the other hand, if the two springs are in series, then the displacement in one spring, say K1 and K2, two springs are in series, then the displacement in one spring may be different, say if it is delta 1, and in the displacement in the second spring, K2 may be delta 2, and then the total extension will be delta 1 plus delta 2. But if that takes place under a force P, PP pair we are say applying from both the sides, then that P is common. P is acting both in K1 and also in K2. That means, you see, the stiffness becomes, what is delta 1? Delta 1 will be then, in that case, P is same, so P by K1, and delta 2 will be P by K2. Therefore, delta 1 plus delta 2 will be P by K1 plus P by K2. Okay, and then as a whole, if I try to see what is the equivalent stiffness, then it should be P divided by the equivalent stiffness K equivalent. So P by K equivalent equal to P over K1 plus P over K2. So if you cancel P from all the sides, I mean from both the sides, so you get 1 by K equivalent equal to 1 by K1 plus 1 by K2. So here you see that both of them are together resisting the motion. That means they are acting as if they are in parallel. And that means it is becoming equivalent for this particular mode. This is becoming equivalent to a system that 2m mass and 2k stiffness. So it's a single degree of freedom system where the mass is 2m and stiffness is 2k. So omega 1 becomes, and the natural frequency, I mean, if we explain it from this physical point of view, that also becomes 2k by 2m. So it's equal to k by m, square root of k by m. Then in the second case, they are trying to move in the opposite direction. That means moving, they are, say if I draw a line through the middle of this spring, that means about this line, the movement is symmetric. This M is moving in this direction, this M is say moving in this direction, or this M is moving in this direction and this M is moving in this direction. So how physically we can look into it? If I I can consider that, well, half of the spring of this particular spring is acting for this mass, and half of this half of this particular spring is acting for this mass. Then can you tell me what will be this stiffness? If the stiffness of this spring is K, then what is the stiffness of the half of this spring? Ask you the last question, which I haven't shown here. Now say if a situation come in this situation, like you go to the previous figure, I mean the original figure, here if this spring we remove and if this spring also we remove, then what will happen? Then what will be the natural frequency and mode shapes? If you can tell it, I'll understand that, well, so much we are discussing about structural dynamics, at least some of the effort is really works. Everything is not in vain. Now give a gentle push to this system, then what will happen? You try to understand. Initially, because of the inertia of this mass, when you will give a push to this mass, then this spring will compress, and that will start a vibration. But at the same time, then this spring and then these two mass, M and M, they are riding on a frictionless system. Therefore, they will move as a rigid body. That means they will keep on vibrating with respect to each other. At the same time, this whole thing will undergo a movement. When we talk about the natural frequency, when the motion is repetitive, okay, frequency means the number of cycles the system is performing during vibration in unit time. Okay, or
Yes, sir.
that means that may be in terms of the radian, or that may be in terms of the, if we can use
Rotation
it in
per
terms
minute.
of cycles. Okay, so cycles means hertz, so we will divide the whole thing, whatever omega we are getting, by 2 pi, then we'll get cycles. But I mean just one and just same way of expressing the things, just in two different ways. Now that means, you see, when these both of them will keep on moving, that means there is no repetition of the motion. So the number of cycles performed in unit time is zero because they are moving. So the first natural frequency is a zero frequency, and first mode shape is a rigid body movement, there is no end to it. While the second mode shape, second frequency will be there, which can be calculated, and if from this equation, by putting the things rightly, the value of the k's adequately, you can find out the second natural frequency and the second mode shape. And this is exactly why I take this problem, because this is exactly happens for an aircraft. When an aircraft is moving, then it is moving as a rigid body. Or a missile is moving, it is moving as a rigid body. So the first natural frequency is zero. So when we will solve this problem, if we just, get shocked by the first natural frequency, it is coming zero, we are not getting any motion. Then, but we see that even if you just out of curiosity, I just notice all this. You see, if you even the wings, you will see that visibly vibrating when it's in air pocket. That means, and then the body is also vibrating, it is undergoing pitching, yawing, rocking, all kind of stuff. Okay, and of course, rocking is much more. Uh, so that means these are the next modes or next natural frequencies. But the first natural frequency is zero. And that's how we should, and then there can be, I mean, the vibration is so complicated, then there can be a large number of mode, but the first mode we cannot define properly, and first natural frequency is zero. We have to eliminate them. There is a sweeping out procedure. We will, if possible, we will discuss this uh, in this course. So we have to eliminate that, and then with the rest of the part, we have to make again an eigenvalue problem analysis. Do you get my point? So this is a very practical problem. Uh, that, I mean, if somebody suddenly asks you that what is the fundamental frequency of an aircraft moving in the sky, then the simple answer will be the frequency is fundamental frequency is zero, and then the fundamental period is, that means, infinite, because it will come back after infinite time. It will not come back to its original position again, because the second frequency is there. See these two masses. These are zero, but they are coming. This spring is compressing and extending. When you have given it a, you have given this mass a push. This mass was not in a mood to move. So suddenly, when this mass moves, then a compression is created in the spring, and that means some strain energy is accumulated, and then that gives rise to a vibration. That means because of this compression, then it will push this mass, and then when this mass will go to some extent, then again this spring will try to pull it back. So that way these two mass will keep on vibrating. I mean, they will keep on coming closer and moving away from each other. So this is the beauty of the problem. And until and unless you understand the physical significance, only the mathematics is a language of physics, but then your knowledge will not be completed. And you will not be able to apply this knowledge. This basic knowledge is being applied to analyze an aircraft. Just try to imagine or analyze even the structural behavior of a missile, which is, and at the same time, the missile is having a problem that it is subjected to very high temperature, where the material behavior becomes different. The stress strain curve, everything becomes different. So that's how we are just thinking about the practical problems, and it's really, the mechanics is really exciting. Okay, so then we can call it a day.